Section 2.5, Newton's Laws of Motion. In 1686, Isaac Newton presented his laws of motion in the book Principia Mathematica Philosophiae Naturalis, detailing the forces acting on a body and the motion of the body. The first law of motion says a body will not change its motion without a force. This law is also known as the law of inertia, and it postulates that if a body is at rest, or if the body is moving in a straight line, it will remain at rest, or remain moving in that same direction, unless it is acted upon by a force. That first law is also known as the law of inertia. The body will not change its motion without a force. The second law of motion says that the acceleration of matter depends on two variables. One of the variables is the force that's acting upon the matter, and the other variable is the mass of the matter. So we have force acting on the matter. In this case, it's a rocket with mass. And the acceleration is, we can see that vector is in the same direction as the force vector. The equation with the symbols that represent that second law of motion is F is equal to ma. M here is the mass, A is the acceleration. The object accelerates in the direction of the force. The third law of motion is also known as the law of action and reaction. It states that when two bodies interact, the force they apply to each other is equal in magnitude and opposite in direction. As we can see, the woman on the floor pushes down the floor. There's a force pushing down due to the weight of the woman. And of course, there's a force that's pushing up on her due to the third law of motion. Now let's talk a little bit about momentum. Momentum is a tendency of an object to keep moving in the same direction unless it's acted on by an external force. This momentum is directly related to the object's mass and the velocity. And because it's related to the velocity, momentum is a vector quantity. The letter P is the symbol that's used to represent momentum, and it's a product of the mass multiplied by the velocity. The mass up here in blue is the mass, the units must be in kilograms, and the velocity is in meters per second. So let's say we have this car that's driving down the road at 50 kilometers per hour. And then there's a bus also traveling at 50 kilometers per hour. We can ask the question, if the speed is the same with the car and the bus, will the momentum be the same? To answer this, let's look at the momentum equation again. P is equal to mv. M is the mass and v is the velocity. We see that both the car and the bus have the same velocity, but they do not have the same mass. The bus has a larger mass than the car, so the bus has a greater momentum than the car. Now here are some momentum facts. Momentum is a vector quantity. That means that it has magnitude, a number with units, and direction. The unit for momentum, when we're given the mass in kilograms and our velocity in meters per second, is kilogram meters per second. Therefore, the unit for momentum can be written as kgm over s, or kilogram meters per second. Another momentum fact is that the larger objects, which have larger masses traveling at the same velocity than a smaller object, will have a greater momentum. Now let's talk about objects moving in a circle. Do you know that a force is needed to keep that object moving in a circle? That force, represented by F is called the centripetal force or centripetal force. And as we see before, the force pulls on the object and keeps that in that turning motion. And together with that centripetal force or the centripetal force that's directed towards the center of the circle as the object is traveling in that circular motion, we have A, which is an acceleration towards the center. That force is described by the equation where F is the force is equal to mv squared over r. M is the mass of the object that's actually spinning. In this case, it's the ball. V squared is the velocity, and r is the radius, which we see in the picture. Now, from Newton's second law, we saw F is equal to ma. When we compare both equations, we see that the acceleration, A, which is a centripetal acceleration, is v squared over r. This motion is also used to explain how satellites stay in orbit. Instead of having ball, we have the Earth, which provides a gravitational force, and that force pulls the object towards the Earth. That's the centripetal force, which is equal to the weight of the object as it's attracted to the Earth. The object that's spinning could be a satellite. In this case, I have the ISS. You see that the radius, the acceleration, velocity all stay the same. And so the thing that's keeping the satellite in orbit is actually that centripetal force of the Earth pulling on it as it moves in a certain radius around the Earth. So we know that g is the acceleration due to gravity, which should be the acceleration that corresponds to the force or the gravitational force of the Earth. So for a satellite, A, or the acceleration, is equal to g, and so g is equal to v squared over r. So g, which is the acceleration due to gravity, times r, which is the radius of orbit of the satellite, or in this case, the ISS, is equal to v squared. We can get the velocity or the speed at which the ISS is orbiting the Earth by taking the square root of the acceleration due to gravity multiplied by the radius of orbit of the satellite. This takes us to section 2.6, which is Newton's law of gravitation. Newton's law of gravitation says that every object in the universe is attracted to every other object with the force that's directly proportional to their masses and inversely proportional to the square of the distances between them. So the two key notes there are this force is proportional to the product of the masses, which means those are the masses that's multiplied together, and inversely proportional to the distance. That means as the distance gets bigger, the force gets smaller. So if we go back to our picture where we have an object in orbit, the force, so gravitational force, is equal to the gravitational constant multiplied by the mass 1 and mass 2, which in this case will be our Earth. Mass 2 would be the mass of the ISS. And d squared is the distance between the Earth and the satellite. In this case, it's known as the radius. So we see that as this distance between the objects increases, the force gets smaller. And as the distance between the object decreases, the force gets larger. This brings us to the end of chapter 2. Thanks for watching.